it's always great fun to be here. I think I'm the oldest TIFR guy here around, I think. No, Gautam was there actually when I came. So I think Gautam has been around. I think he was a student when I came, right? Okay. Okay. Okay, so I'll talk about some work which we recently did, which I would like to characterize, kind of a phenomenological understanding of this SYK model. Okay. But I'll begin with some very general remarks, which I think some of the younger people may not be completely aware of. So the whole idea that you can somehow generate space-time from internal degrees of freedom is actually a very old idea, and probably one of the first concrete proposals was made in a very famous paper by Eguchi and Kawai in 1980. And what they did was something quite remarkable. So they took lattice gauge theory, which is the right hand side of this equation. This is the Wilson action for lattice gauge theory. These are the link variables on some regular lattice. And they say that large n, I can completely forget about the fact that there is an x dependence, namely that it's actually a lattice in space-time. So basically they were saying that this at large n can be replaced by a matrix integral over, if it is a 4-dimensional gauge theory, matrix integral over 4 unitary matrices. So there are many versions of this kind of correspondence. I'll just mention very briefly one of the versions. So you might wonder, where does this x, I mean, after all, there has to be a x somewhere, because I have some Wilson loop. I have to tell you how to compute that. And this is something which is called the twisted Eguchi-Kawai prescription. So what it does, it says that take a link variable. So u mu of x, by notation, there is a point x mu, x nu, there is a link direction in the mu direction, and this variable here is a unitary matrix u mu of x. So the idea is that that object is related to this pure unitary matrix u mu by this conjugation by another unitary matrix D, and this D is a product of something which are called étouffed matrices. And this you take a product of this étouffed matrices and raise it to that x which was here. So that's where the x comes. So in somehow you take these étouffed matrices are defined by this. These are called twist matrices, so which have this particular relation. So the idea is that all the information about the étouffed matrices is sort of encoded this object D, and therefore you can use that to calculate any arbitrary Wilson loop in the gauge theory.
So n is the rank of the gauge group, right?
N is the rank of the SUN gauge group, UN gauge group here. Yeah.
Sumit, this is supposed to be good enough to give us n-point correlators in the large n limit? That is the statement that in the large n limit only the 2-point function survives, and then maybe the
No, these are general Wilson loops,
so
right?
Yeah,
You take any Wilson loop and this will evaluate for you any Wilson loop. So in the large n limit, the whole point is that, I mean, you can always derive a Dyson-Schwinger equation for the Wilson loop. These are called the loop equations, and usually the right hand side. So if you take a Wilson loop is like a trace of some unitary matrix W, which is a product of the link variables. So there is some operator acting on this thing on the right hand side. So its expectation value of that is usually a trace WC1, trace of WC2. I'm writing in a very rough fashion, this kind of thing, and large n comes by replacing this by trace of WC1 times trace of WC minus C1. That's where the large n comes in. So yes.
What is that raising? You need to understand.
This raising. So x mu on a lattice is a set of some integers. Each point x let's say 4-dimensional, there are 4 numbers here. So, what you do, you take at that point, what you do is you and nu gamma nu, there are 4 gamma nus. So, take a point x, take a product of these gammas. Oh, I mixed up the indices, gamma nu to the power x nu, okay, okay, and raised to that particular product. It is a particular unitary matrix which you are associating with a point. Okay. So, now this is quite a fascinating proposal, and of course, a lot of people worked for several years. There has been recent very interesting developments by these papers of Koftun, Munsal and Yaffe in 2007, which actually made this really workable in certain contexts after a very long time from 1980 to 2007. One problem is that it only works strictly at n equal to infinity. The finite n corrections to this entire procedure are not under control. It is not something one does not have a systematic way of computing 1 upon n corrections to this thing. I would also like to remark that BFSS matrix theory or IKKT matrix theory are similar in some respects. It again takes matrices and sort of constructs space-time out of it.
Reason the large anything, is there a way to understand why 1 over n cannot be easily computed within where this factorization is so important?
So, factorization is certainly important, but you can compute it is this plus 1 upon n times something. So, in the naive ways of writing this, this computed in the lattice gauge theory does not agree with what it is computed in the Eguchi-Kawai model. That is the statement. It does not mean it cannot be fixed, maybe it can be fixed, but I do not think anybody has really addressed that issue. Okay. Another example, another very well known example solved in a very famous paper by Brezin, Itzikson, Parisi and Zubair, again around 1980 or so, is the quantum mechanics of a single matrix. So, what you have is a single Hermitian matrix Mij in action formalism. It is a dynamical variable function of time, and in the singlet sector you can encode all the information about this into something which is called a density of eigenvalues, which is defined in this particular way. And it turns out that so doing this, you go from n square variables, which is a function of time, to a single variable which is a function of this fiducial thing x and time, right. The n square is all gone, and it turns out that the space of eigenvalues x is related to the space on which 1 plus 1 dimensional string moves. And this again has been pursued very vigorously by many people in the 90s. It was a popular thing. Now, 2-dimensional string theory is sort of interesting, but it is not that interesting. It is interesting in the sense that it has a black hole, famously discovered by these guys and by Witten. However, that black hole, I mean, and one always wanted to understand what is that black hole in the matrix language, and one never really put its finger on it. You know, it's something, there is a complicated description which is not in the singlet sector, but once you go out of the singlet sector, the theory is not solvable. So, that is not very nice. So, that is another frustration. Now, most interesting setup for holography is of course the ADS-CFT correspondence. So, here what is this?
ICTS has just requested to be in on it. So,
Will they hear the talk last week?
but they nevertheless want to hear it again.
Well, flattering. Okay. So, the most interesting setup is ADS-CFT correspondence, where there is a 3 plus 1 dimensional field theory at large n, which becomes equivalent to a 10-dimensional string theory. So, there are 6 dimensions which are generated. They are slightly generated slightly different ways. One is generated from the internal R symmetry groups. another one is generated by some scale transformation, things like that. But nevertheless, at the end of the day, there are 6 additional dimensions which are generated. However, there is actually very little hope that one will be able to understand the explicit map which takes you from this 3 plus 1 dimensional theory to the 10 dimensional string theory. If we of course had that, then like we will be very happy, but that's too much to expect. So from that point of view, and I should also make a comment that the previous slide, the matrix quantum mechanics, is in fact very closely related to the ADS-CFT correspondence, and this was realized maybe about 10 years ago by McGreevy and Verlinde, and it's Klebanov, Seiberg, and Maltasena. So given this context,
See, I should know this literature, but I thought even VFSS to begin with was very much zero-grain quantum mechanics and some limit, but these people made it more precise.
no, this is actually the matrix, the C equal to 1. So they cast the C equal to 1 in terms of d-branes of the string theory. So it's closer in spirit to this thing. Okay. So it's clearly useful to look for solvable models of holography where we understand how this happens. So this, in Coleman's words, are recognizable caricatures of the real thing. So that's always useful in theoretical physics, and so that's what we are going to pursue. And I should mention there is a complementary approach to understand this, is to connect the emergence of space-time with quantum entanglement and complexity. I mean, what would be really great is to sort of merge these two ways and having a really concrete example of how this works. That's what I would really love to do. Okay. From this point of view, models with scalar fields, say for example fields in the vector representation instead of adjoint representations like the matrices and so on, are usually solvable at large n.
Just,
Yeah.
So there are also, of course, these things like Chern-Simons theories, which are topological theories.
That's
and
right.
The only physics is there in the boundary. So therefore, I mean, somehow it's automatically a boundary theory already.
That's right. Yeah.
So that's another kind of correspondence in which one higher dimension, although in a sort of strange way, it's just it's not as if not there at all, but it just pops out.
Yeah, but in all the other examples, there is genuine bulk physics. I mean, there is gravitational waves, there are propagating degrees of freedom in the bulk which are reconstructing from the boundary.
Perhaps
So
one has not discovered that big gauge symmetry which makes the additional dimensions trivial.
Could be. Could be.
That, the Chern-Simons to Weismann-Witten
Yeah.
is like ADS3 CFT2 kind of correspondence, which is part of the family of ADS CFT, except it could be something very, very singular. But
yeah, I think you may be right, because I mean in some real sense theories of gravity don't really have diffeomorphism invariant bulk degrees of freedom in a way. I mean everything somehow.
Yeah.
So maybe there's something, but as it stands, they sort of look a little bit different, right? I mean, from normal ADS CFT.
Are you saying for 2 plus 1D gravity? Is that?
But 2 plus 1D gravity, is more or less in the spirit of, because
That's right.
2 plus 1D gravity can be recast as SL, SL2 cross SL2 Chern-Simons theory, and it becomes like the theory of this boundary gravitons, and including even gauge fields in the bulk and so on. So of course it's true that it can be completely different and qualitatively different from ADS4 CFT3, for instance, in which they are propagating gravitons. But it's also true that it's always so hard to talk about any local physics in a gravitational theory anyway.
Right.
So maybe the correct gauge invariant, there's some. Well, this issue of course is being hotly debated. I mean, whether there can be.
It could very well be true. I mean, maybe the things which we call theories of gravity could be gauge-fixed versions of something which is a higher level of symmetry, and so that is sort of hidden. That could very well be true. I think. Yeah. Good point. So, so they have been sort of useful in understanding the origins of holography, though not in a very physically interesting situation, because the theories as Klebanov and Polyakov conjectured, the simplest versions like conformal ON vector models, the bread and butter of condensed matter physics or statistical mechanics, is in fact dual to something called a higher spin gauge theory. So, these are theories which have gauge fields of all even spins, and all of them are massless. So, from that point of view, I mean, it sort of addressing questions of locality in the bulk becomes a little bit tricky. But nevertheless, these are examples of holography, and in that context, quite some time ago, I mean basically after this paper, we made a very naive proposal, and the proposal was roughly as follows. So, phi I is a field in the vector representation of ON, and then what you recognize, all the invariant objects which you can make in this theory are necessarily made out of these bilocals, because you have to contract the index once. So, everything can be written in terms of these. So, one might make a change of variables from the phi's to the psi's, and this change of variables and the Jacobians and all that, there are well known techniques which were developed by SYK and Sakita back in the 1980s. And so, what you have is basically a theory written in terms of these bilocals. And then we said, well, let us do the following. So, there are 2 points x and y in some d dimensions, and you construct the center of mass and the relative coordinate, and then you break up the relative coordinate in a polar decomposition. G is the magnitude of this v, and these are d minus 1 angles. So, it is like writing a vector in terms of its radius and some angles. And then we thought that, well, look at this, one aspect of ADS CFT is that the scale in the boundary theory actually becomes an additional dimension. So, we thought, oh, it must be that this object z, which is the scale, must be the Poincare coordinate in ADS. Okay. And bluntly, it does not quite work. It does not quite work in d dimensions, because if it did work, then I could have made a conformal transformation of the x and y and look at what it does to u's or some fields. So, what you do is like take that bilocal field and you break it up in terms of spherical harmonics of these angles, and what you get is a set of spin fields in one higher dimension. Okay, that is what sounds like Klebanov and Polyakov. So, conformal transformations of x and y will induce some transformations of these fields, and those transformations should agree with what conformal the killing isometries of ADS would lead on phi's. Okay. So, let us see what happens. So, I have written translations, dilatations and rotations. This sigma should be that curly phi. I mean, this is some just copied out of a paper, so I think I did not change the notation. These are what the transformations are. So, these the right hand sides are obtained by performing conformal transformations of x and y, and therefore, conformal whatever transformations of u and v, and plugging that in. And what you note here is that they are in fact exactly how these fields of a particular spin will in fact transform in an ADS space. Lij are the angular momentum generators in this in d dimensions, and they appear as a spin, an internal quantum number when interpreted as a theory in ADS d plus 1.
So, what are the theta ij's?
So, these are parameters. This is t, and theta ij's are the parameters of the rotation here, omega ij's.
Oh, okay.
Okay. But it does not work for the most important conformal transformation, which are the special conformal transformations. And the simple, so the first line here is exactly what you would expect from ADS. The second line is not. In fact, as you can see, it's very easy to see that in the second line, what it does, it mixes fields of different spins, and that's not what you would expect for a set of spins in spin fields in ADS. Now, we did notice that it actually curiously it works for ADS2, and I'll show you explicitly why it works for ADS2, but then we thought that, wow, who cares about ADS2? We are interested in ADS4, which is the three-dimensional conformal ON model. So, we didn't think about it very much, and I should make a comment that these are in the Euclidean formalism or with space and time treated in the same way. You could do the same thing for bilocals which are equal time. These are relevant for theories where the large N symmetry is gauged. You only want to write wave functions which are functions of the singlet variables. Now, it turns out for d equal to 3, these people, Di Mello, Koch, Rodriguez, Javicky and Jin actually corrected this situation by inventing a non-local transformation such that everything works. The resulting formalism works, but it is really messy. You have to go to light front gauge and all that. It's not something which is something very natural.
When you say non-local, it's still the bilocal field, but the transformation.
So, you take this bilocal field, interpret it like that. You interpret, take these. It's a non-local transformation on the u and the z. Okay. It's, I think, this is something which Subrat pointed out. This could be just this. What is this? HKL transformation in some way. Okay. It could be something like that. I don't know. I think it is. It couldn't be anything else.
But even with all that, did it really work eventually? I mean,
well, they could reproduce 3 and 4 point functions of this Giombi and Yin, so to that extent. 3 point functions, yeah. 3 and 4 points, I don't know. I think 4 point functions also. I don't know, I really didn't follow that. But it certainly worked for conformal transformations. I mean, the transformation property certainly worked. They derived that kernel, in fact, to precisely reproduce the conformal transformations. Okay. Yeah.
but so let me see. This works for ADS2 means that.
So,
there
next
is no
slide, next slide.
There is no sphere there.
There is no sphere. So, this is ADS2. So, we started d equal to 1 theory. Okay. So, just t I am calling. So, x and y, no vector indices. So, these are L minus 1, L 0 and L plus 1, for the transformations for x and y, and you combine them, you define x plus y and x minus y, and you combine them, and then you find these are precisely the killing isometries of this matrix, and quite curiously it is a Lorentzian metric. I don't quite understand why. If you take the plus sign, it is not going to work this way. Okay. So, I never understood why, but that is the way it works. It is precisely the right transformations of ADS2. Yeah?
You commented something on that the ON to Vasiliev to
Uh-huh.
we cannot understand much about the locality of the bulk.
No, you cannot.
But anyway, the observables in the bulk side need not be local, right? Only good observables in the bulk side. Why do you want locality?
You don't know. It is not a question of observables. We want something where there is we want a theory of gravity where there is a scale, and below that scale the physics is local, right? And I think the Vasiliev theory doesn't have that. It's non-local at the ADS scale. You don't want a theory which is non-local in the ADS scale. Okay. There has to be an alpha prime which controls that. There is no alpha prime in the Vasiliev theory. In that sense, it is less interesting than ADS CFT of string theory, I think. Okay. String theory has that. Okay. Okay. So, this construction has been recently used to understand properties of this very fashionable thing called the SYK model. Okay. Actually, I don't know why it is interesting from the condensed matter point of view, but apparently it's very interesting. So, let's assume it's very interesting. So, it's a model which is not quite a quantum mechanical model, because what it does, it takes a Hamiltonian and then treats these couplings as random couplings. And I actually know very little about this model. So, I think I will just state the results which I have read in various places. And so, one way of dealing with the randomness is to use the replica method, and apparently Kitaev showed that whatever you do, when you have a large number of these indices, it is always replica diagonal. Okay. So, that is what apparently he showed. So, I will assume that. To leading order in large n, that is apparently what he proved. So, saying that, we can clearly define a bilocal field which is obtained by this, where i's are now become an internal index. If there are n of those, to begin with, it was not an internal index, it was just n Majorana fermions which are interacting with each other. But now in this, you can treat these i's as an internal index, and this is an observable, a bilocal observable which you form, where implicitly I have also contracted the replica index here, but the replica index does not play much of a role in this entire story.
So, T1 and T2 are time?
T1 and T2 are time of the, because that is what the Hamiltonian is, that is all there is there. Okay. And then what these people did, use the same technology which makes a change of variables from the chi's to the psi's.
Just a little confused about the internal index remark. I mean, this SYK Hamiltonian taken as such.
Yeah, does not have any SUN symmetry.
Single site object, just quantum mechanical particle with multiple flavors.
Right.
IJ, etc. Flavors or colors depending on whether you are gauging it or not. But so therefore, it is an internal index.
But there is no symmetry to begin with, because J, I, J, K are random couplings. It is only after you perform the averaging over the random couplings that.
I am saying there is no space time associated.
No.
So it is internal in the sense that it is not.
Absolutely right. I should have said not internal, but internal symmetry index. I mean, it became a symmetry index after doing all that. Okay.
So, for local parts like T1 equal to T2, it's a trivial number, because chi-square is 1.
Yeah.
For T1
That's right.
equal to T2 in this Majorana model, it doesn't exist.
Yeah, doesn't. That's right. Because psi's are totally antisymmetric. Psi T1 T2 is minus psi T2 T1. Yeah. I should have written that.
So
Yeah.
I'm saying for T1 equal to T2 is 0.
Yeah.
Because Majorana.
But for general T1 T2,
Chi-square is 1.
No, that's not it. It's Majorana.
So, in the four-way, in the standard Majorana, the chi-square goes to
No, it's a single Grassmann variable.
single Grassmann variable.
It's a single Grassmann variable, square is sigma.
And this is the general relation. It is antisymmetric under interchange. Okay. So, it can be written as a path integral over these things. Forget about this mu of psi, that is only important to 1 upon n correction. And there is an what is called a collective action. This is the action which provides the dynamics, and I have written out that collective action. This piece and that piece is, this piece is just the kinetic term of the fermions. That piece is it was like a 4 fermion interaction. Once you integrate over the J, that gets converted into an 8 fermion interaction. So, that just organizes themselves as psi to the power 4th. This is a Jacobian which comes from the change of variables from chi to psi. The equations of motion which are obtained by varying this action are the original Dyson-Schwinger equations of that model, which you could have derived by summing over ladders or what have you. Okay. So, this I have written down what are the Dyson-Schwinger equations. In general, this Dyson-Schwinger equation cannot be solved, but it can be solved for large J. J is an object in the theory which has dimensions of mass. So, large J means the infrared behavior of the theory. So, in the infrared you can solve this, and this is the solution. The way to see it is you can rescale the psi by some power of j, and then you can see that this is 1 upon j compared to the other ones. Okay? And this is the solution, and this tells you that in the UV, that like in the free theory, this object psi was dimensionless because chi was dimensionless, but in the IR it has acquired a non-trivial anomalous dimension, as is clear from here. Okay. So, that is the picture. So, there is a conformal invariance which is regained in the IR. In fact, it is stronger than conformal invariance because it actually a full reparametrization invariance which is actually achieved at IR. So, in the spirit of a large N theory, that was the saddle point solution of this equation. So, what you got to do is to take a fluctuation around that saddle point, expand the action and compute various quantities that would generate the large N expansion of the theory. So, I have written down that split, and then I take that fluctuation and write it in terms of suitable modes. The suitable modes is a Fourier mode in time and a function of the other coordinate z. This coordinate z, remember, is something which I invented. I invented by I didn't know what z is here. This is the relative t1 minus t2 if you wish. Yeah, I have written x and y, and time is the average. And this function is a combination of Bessel functions which was obtained by Kitaev and by Polchinski and Rosenhaus. This combination has the property that is, first of all, it forms a complete orthonormal set of the Bessel functions. They all are so they are normalizable, and they vanish at z equal to 0 at when the thing is 0. And the reason why it vanishes, you might wonder how come it vanishes, because there is j minus nu. The set is formed by when nu is real, it is of this form, and the other part is nu is purely imaginary when nu is I times r. Of course, when nu is I times r, j nu and j minus nu are nothing very different near x equal to 0, and when nu is real, it has to be these values, and for those values this factor vanishes, and that is the reason why these are normalizable. I do not have much of an intuition about why these things are important, but I just took those because that is the one that diagonalizes the kernel in the Dyson-Schwinger equation for the fluctuations. Okay. That is what Polchinski and Rosenhaus very carefully did. Sure.
And just to make it a little clear, in my mind, the z coordinate which was acting nicely in these conformal transformations is also the one standard z coordinate in AD.
That is right. So, that is what this slide shows. Okay. That is what that slide shows. This one. Yeah. Okay. This comment will be important because this is one of the things we do not completely understand why we need to do this. We will show that this slightly, it is a little bit different from standard ADS CFT. Okay. A little more about these functions. This is the normalization condition, this is the completeness condition, and this is the normalization factor for these various things. They are all possibly derived by Kitaev, but who knows, because he never writes a paper. So, but anyway, okay. I will write in various places this notation which is an integral d nu upon n nu. What it really stands for is a shorthand for the sum over discrete modes and an integral over the imaginary values, so integral over the imaginary axis. Okay. So, now we have all set up, substitute that, and in the action what you get is those things which were the modes obtained by expanding these objects, and there is a sum over nu and omega. This sum means also an integral over the imaginary values, and you obtain this inverse propagator in that space, which is given, this function is given by this object. Okay. So, the zeros of this gives you the spectrum of roughly the anomalous dimensions of the theory. And here is a graphical solution of this equation. So, these are these tans. I have written these are tan as tan equal to minus nu, and there are infinite number of points. There is a 0 here, but there the wave function sort of varies. So, to take out the 0 and just this is infinite tower of things.
Little confused about these imaginary news. It's not true that the small fluctuations literally correspond to the conformal primaries in the boundary in the SYK model. That is, you only get real news of the right dimension.
No, so it's sort of written in a different way, because this to do that you have to do the integral over nu. So, going to on shell. I'll show that what happens in that case. In fact, there is a very interesting cancellation that happens. Okay. Good. It will happen. So, in fact, this is what it is. Okay. So,
It's completely omega independent, the inverse propagator.
yeah, it's sort of hidden in the phi tildes actually in a way actually. Yeah.
In the way you have chosen.
In the way you have chosen. So, the 4-point functions of fermions at large J has been calculated by many people in various ways. In this language, it's just the 2-point function of the bilocals. That is how people calculate it. And what I have done here is taken that propagator, that is 1 upon this function, done the integral over nu. Okay? And if you do the integral over nu, with a long story short, this is what you get. You only get a sum over the solutions of the equation tan, Pm are solutions of this equation. Okay? So, this is the result. There is a horrible factor here which involves those things. That factor is nothing but the residue of the poles. If you calculate the residue of that function at the various poles, and this is the LoRa expansion, roughly speaking, of that. Okay? So, this is something we want to reproduce in some way. Now,
So I guess probably what I was getting wrong even in the intuitive picture is that collective field theory is of course the full off-shell theory, and then you look at the on-shell conditions and that reproduces the condition.
absolutely, that is right. That is the integral over nu, if you wish. Okay. I would like to make a comment here that is object phi of Tz, which was the this object, looks like a single field in 1 plus 1 dimensions, because after all in my general discussion I said, like if I had d dimensions, you have a whole tower of higher spin fields. There is no spin in 1 dimension, so just one field. So, how come you came an infinite number of poles of the propagator? Of course, what is happening here is that even though it is a single field, the field action contains an infinite number of derivatives. Okay. So, it is a very non-local thing, and if you write down an action with infinite number of derivatives, then you can either think of a single field with an infinite number of poles, or you can think it of an infinite number of fields. And this result would be obtained by integrating out a lot of the fields.
It will self-correct.
Okay, good. So, in fact, the form of the propagator looks like a sum of contribution from an infinite number of normal fields in ADS. That is what it looks like. Okay. So, that is why people interpret this, that there is a tower of these fields in this theory. Okay. The anomalous dimensions of the corresponding operators, the dual operators in the boundary theory, in terms of the Pm is given by this formula. If you recognize, this is the d upon 2 of that famous ADS formula. Okay. And the Pms are the analogues of nu, that is why I also use the same notation.
Can you explain this a little bit more, going back to the previous slide a little bit? Yeah, so, okay, so this is the propagator for the phi.
Yeah.
And okay, so the RPM fellows, they have
These are functions of Pm, which is written here. They come from the residues of the pole.
so the poles are at nu equal to
M. Actually, there are a lot of things actually, so maybe I should go into this a little bit. So, there is an integral over nu by d nu. Okay. This integral stands, first there is a sum over nu equal to 3/2 plus 2n, and then there is a term which has an integral over I dr n of I r. That is an integral over the imaginary axis. Okay. And there is some integrand here. Okay. The integrand is complicated because there are all kinds of Bessel functions, some combinations of Bessel functions. Okay. So what you do to this one, you close the contour on, it turns out that the form of these Bessel.
Is related to nu, like nu is equal to something plus IR, right? Or
No, nu equal to IR, I just wrote.
nu
Or,
itself is equal to IR.
yeah, nu is itself. Or imagine, or just write it as in the complex plane, write it as an integral over the imaginary axis. Okay. So in order to figure out how to close the contour, you have to look at the integrand and see how it behaves at large values of z. And it turns out that what you need to do is to close the contour this way. Okay. And then you have to figure out the poles which are inside this contour. There are two sets of poles here actually. There is one set of poles which come because this z is this combination. This quantity actually has poles, these I news have some poles, and these poles are actually a 3/2 plus 2n. Okay? And then there is a set of poles which come because you are in that integration, somewhere there is this object g nu minus 1. Those poles are the PMs. Okay? So there are some set of poles, and then there are other poles which come from these. It turns out that the contribution from those ones exactly cancel this sum, and all you are left with is a sum over the zeros of this function. Those I am called PM. RPM is the residue at those poles as calculated from that function. Okay? So basically you take derivative of g nu, g tilde nu and evaluate it at PM.
Since you're explaining it, seems like a bit of black magic, but if you're not chosen to expand in terms of j nu plus I, j minus nu, I mean this is a math step, right? Or
It's a math step.
Input there that the fluctuation has to satisfy some boundary condition.
You could have, for example, I mean just to, let me come back to that comment when I discuss the phenomenology. It's an important comment. Okay. Okay. Good. So let me proceed. I'll come back to this comment actually, because this is one of the things I don't understand. So I think I'll
In
tell
your
you.
language of more and more derivatives, actually, is the PM rating the number of derivatives?
PM. PM are the zeros of this function, the PM are the solutions of this equation, but you know this function when you write it in terms of this nu is an eigenvalue of an operator which is like a Bessel operator, this operator plus something. So having a non-trivial function of nu is kind of having a non-trivial function of derivatives. That is why it has higher derivatives. Okay. So our main aim is to understand where does this come from, what does this actually mean, I mean what is there a meaning of this infinite tower of states or this of this magic formula which have there. I should make an important comment here. There is a special mode which we call m equal to 0, which is p0 equal to 3/2. It is a solution of that equation. Okay. At strong coupling, this is a 0 mode of diffeomorphism invariance in the IR. So basically, we take the saddle point solution, perform a diffeomorphism on that, that is what you get, this particular one. We could have included this mode in the sum. I did not include it in that sum because I just copied something from some other paper which I did not write. It's a sum from m equal to 1 to infinity, and the reason I did not include it, because normally what one does is to separate out the 0 mode, and it is not a 0 mode at finite j, and one derives the dynamics of that mode, particular mode at finite j. It turns out that dynamics is governed by a Schwartzian action. That is one of the important things about this. However, this is all at infinite j and the leading j expansion. Maldacena and Stanford also calculated what is the correction to this formula at finite j in a 1 upon j expansion, and they got a formula which is like this. This is this 3/2, and there is a thing which has a frequency divided by j. Okay. In a sense, the correction had to be an expansion in omega upon j, because there is nothing else there. I mean, j is a quantity of dimensions of mass, and the only other thing which is there is the frequency. So, we would expect that if you are doing an expansion in 1 upon j, it is probably an expansion in omega upon j, and this is the first term.
At 0 temperature.
These all at 0 temperature.
Otherwise there will be another.
Otherwise, there will be other things. Okay.
This confuses me, just from the point of view of representations of the conformal group, what does this mean? Because at any j.
But now you are breaking the conformal group at any finite j.
Is that right?
Yeah,
The
there is
theory
no.
doesn't flow to a fixed point for any finite.
Yeah,
That's
but now
infinite j.
You are coming away from the fixed point. So you are turning on.
Oh, I see.
an irrelevant operator.
Fixed point is at j equal to infinity,
Or omega
J
equals
equals
0.
or omega by j equal to 0.
The way to think of the fixed point theory, I see, for all omega.
Yeah, you are actually here stopping before you reach the IR fixed point
Yeah.
somewhere.
Or you have reached j equal to infinity and you are turning on an irrelevant operator.
Yes,
Which is breaking the.
breaking
So
that thing.
for the other m's, the pm literally was the anomalous dimension at the fixed point. This p0 is not, doesn't have that interpretation, that's what I'm saying. It's not the anomalous dimension of an operator at the fixed point, right? Otherwise it would be strange if it depended
No,
on
in fact that's right. So you do a conformal perturbation theory in the 1 over j operator, and this is what's happening to 3/2. But for every other guy also.
There is also a correction. I've just written down this answer.
There's a correction, but all I'm saying is, normally when we talk of anomalous dimensions at a fixed point, that's not a frequency dependent thing.
That's right.
When you're at the fixed point, you scale time, say, and how do things change, right?
Yeah.
But here, that's not the interpretation.
But I
of
think
PC.
for all the other PMs, it has to be a function of omega upon j, right?
Yes.
Nothing else. Yeah.
No, but what I mean is, you can.
It-
be
it
at the
doesn't
fixed
not an-
point, and you can measure the response of the system as you change omega, scale omega, and that is given by the anomalous dimensions which are independent of omega.
Yeah, but
There are
this
two
is
things.
this is a perturbation theory.
Yeah.
Normally, I think one wouldn't do that. Perturbation theory is an irrelevant perturbation around that fixed point, or in coming from the UV, it's like you have not yet at that fixed point. You have stopped somewhere before that. So you're right. It doesn't have an interpretation in terms of conformal dimensions, I think.
Yeah, I mean it's like a solution of the Callan-Simonzic equation away from the fixed point for gamma. So
Yes,
it's
that's
an
right,
anomalous
yeah.
dimension away from the fixed point. Okay.
It's not gamma of G star, it's a gamma of G.
Exactly. So
Yeah.
gamma of g. So of course it can have momentum dependence,
Sure.
which it has.
Right.
this,
Okay, can I proceed? So what's a little more non-trivial is actually they also calculated the correction to that propagator of the bilocals. And here what I have done, I have taken that formula and taken a 0 temperature limit of that formula. So their paper has a formula, I have taken the 0 temperature limit, and it has this particular expression. What is important about this curly j is the same as this j. What is important about this, that this is proportional to j. Okay. So the thing is at j equal to infinity, we said that this is a 0 mode. A 0 mode should give an infinite contribution to the propagator, and this is that infinite contribution when you put j equal to infinity. So we like to interpret it that way. If you did do a calculation at finite j and then took the limit to j equal to infinity, you should expect an infinite contribution to the propagator, and that's what this is. Okay. So, this they call the enhanced propagator at finite J.
This is done in the q equal to infinity limit. That is why the script J thing came, which is a sort of.
Maybe I copied the wrong. No, there is a formula for q equal to 4 also.
So this here is a particular scaled combination of J and Q.
Is that right?
I think.
No, I think this formula is for finite J as well. I think.
Finite J as well.
Yeah, I think so. Yeah. That's my recollection. Okay. At strong coupling, it is natural to expect that this model is dual to some theory in two-dimensional ADS space, which is ADS2. And there have been various proposals about what this theory is. The gravity sector, it has been proposed it's some version of Jacques-Teitelbaum theory, which has a metric and a dilaton, and there is some junk matter which is nobody knows. Okay.
I thought the junk matter was your whole tower.
Is a whole tower, but what is the action? I think nobody knows. So we are going to make a proposal for that. Okay. The classical actions of this gravity sector, this is a two-dimensional theory. It can always be written as ADS2. You can always choose coordinates. So everything is a 0 temperature, and this dilaton phi then has a solution which looks like this. There is some parameter A, and the z is that Poincare coordinate. A non-zero A breaks the conformal symmetry of the solution, and the natural identification of A is that A is of the order of 1 upon j. Okay.
So with this S matter, of course, in principle, one can like try to construct from
Yes.
the CFT, like
Yeah.
Gross and Rosenhaus have said that okay, these are the 3-point functions which come from the CFT.
Yeah.
So we can invent some bulk couplings which.
And those answers are so horrible that I didn't even look at it. You know, so like it's you can, of course, if you know all the correlation functions, and if you know all the gammas, you can calculate what the effective action
But
is. Okay.
that's not a that's not a first principle thing of finding out. I mean, trying to invent.
Right. Right. Yeah.
Can I ask something? From the gravity point of view, I understand why you need to work with ADS, near ADS and all that. But just from the point of view of the 0 plus 1D quantum mechanics, I didn't really understand this, which is, why can't you consider the conformal field theory in its own right, which you flow to in the deep infrared? Take that you defined a model, SYK model, right, with a J.
So this would be the dual of the conformal field theory.
This would be the dual. But that conformal field theory in the deep IR flows, that field theory in the deep IR flows to a conformal theory.
Okay.
And suppose I'm just interested in that conformal field theory.
That's right. So
what
then
is
it has to be some theory in ADS2,
and purely ADS.
pure ADS2, no dilaton.
No dilaton and
Right,
so on.
yeah.
And I thought, okay, and so what is that theory? What kind of a conformal quantum
No, but
mechanics is
remember
that?
that's a singular CFT because partition function blows up, 4-point functions blow up, and it's all it's a singular CFT unless the CFT becomes well defined only with a regulator. So if you compute the free energy, it's infinity. If you compute
Because of the 0 mode, because there is an exact 0 mode.
yeah, it's an exact zero mode. There is no
So usually maybe there's some peculiarity of quantum mechanics, but usually in a field theory in higher dimensions, if you had a 0 mode, then all right, either it's not then the following may happen. You below some scale, you have a theory of Goldstone modes, and even further below, you have a trivial theory because the Goldstone modes are there.
This is a little bit different.
So the big
Why is
difference,
this
the big
different?
difference here is that there is no pion kinetic energy term at all in this case. Even the pion kinetic energy term actually has a 0 coefficient. In the sense that even
coefficient J.
no
1
it's
upon
pion
J.
mass. There's a pion mass term. So the thing that really makes the theory well defined is the pion mass term. So you have to be away from conformal invariance, okay, and it's only with this 1/j corrections that the theory becomes well
But if you have a pion mass term and no pion kinetic energy term, then I would have thought the equation of motion set the pions to 0.
If you do that, then there is the contribution to the free energy. So let's say that you take the pion mass also equal to 0 in that limit.
Why should I? It's whatever it is.
No, no, no.
G-
I don't understand this analogy, so I think
No.
I cannot
Okay,
say.
what I'm
Maybe
saying.
I'll ask
Yeah.
you later.
Yeah.
Sorry.
Maybe we should discuss this later. I think. Yeah.
Okay.
I see.
Okay. So the gravity sector of the theory is naturally thought as coming from this 0 mode. So this is what people call the soft mode, and then Gautam and Pranjal and Spenta have argued quite convincingly that the correct action for this in fact is the diffeomorphism invariant Polyakov action. My understanding is correct, right? I mean, this is the dual theory for the Schwartzian. Okay. So I'll take a completely different twist on it. I'll do a very phenomenological understanding. I'll invent a model such that I reproduce the answer. Okay, that's what phenomenology is. So that's what I'll do. Okay. So our starting point is to say that this infinite tower of modes is actually a Kaluza-Klein tower, which comes from 3 dimensions. So we said that in the 2-dimensional ADS2 theory, there are infinite number of normal fields with normal derivatives, and what I am going to argue is that that infinite number is actually a Kaluza-Klein tower from a 3rd dimension. The 3-dimensional metric is an ADS2 times kind of a warping of a flat space dy, it's 1 dimension, so what else can it be, except that this y direction is actually an interval. It is an interval which can be thought of an S1 mod Z2, pretty much like Horzava-Witten compactification of M theory. It has a size which I call 2 times L. So, it goes y goes from minus L to plus L, and the scalar, I have a single scalar field in these 3 dimensions with a mass m naught square and a potential, and that potential is just a delta function multiplied by some factor v. So, basically the 3rd dimension looks like this, minus L to plus L, and there is maybe I have a picture of that in the next slide, the delta function potential.
And sorry, Sumit, you also have the scale little a here. Z is Z, I mean,
I'll
minus A over Z.
right. So, that's going to be a non-trivial metric that's in this G here. So, A will be identified with 1 upon J as in the previous slide, right. I mean,
Oh,
the,
I missed that.
yeah. So,
I see.
there was a dilaton. So, dilaton is the metric in the 3rd dimension, and the identification is A is 1 upon J.
Sir, the action in this slide, that's the induced metric, right? On these 2.
No, this is just a 2-dimensional action.
2-dimensional.
In here, this is a 3-dimensional metric.
This is a 3-dimensional metric.
3-dimensional metric, yeah. It's a 3-dimensional theory.
Without
Hmm?
this no root GR kind of analog terms.
No,
Just a scalar in a fixed
I think it should be. We don't know how to treat that. I'll come back to that actually. We're confused about that.
No, I thought that you were taking this in the probe approximately, in the sense that whatever the root GR plus F mu nu square, whatever they have done their job. They have created.
Yeah, but at some point you have to discuss the dynamics of that also, which we haven't discussed. Okay.
And
Yeah.
sorry, you really need the mod Z2 to get rid of unwanted modes. You need the
You need this. You can think of the interval as a circle which is modded off by a deflection along a diameter. So that's mathematicians way of describing an interval. Okay, the 2 fixed points are the 2 ends. Okay. Okay. So to do a mode decomposition of that, I need to tell you what boundary conditions are. The boundary conditions are 0 Dirichlet conditions at the 2 ends, and there is a delta function in the middle which tells you how the derivative of the field, the discontinuity of the derivative of the field in the middle. So it's sort of like this. So, I write the decompose the field. Once again there is this new object. I use exactly the same combination of Bessel functions which I knew reproduce the SYK propagator. I repeat, it is not the natural set of modes which if I was doing normal ADS CFT I would not use those, I would just use the Bessel functions themselves. So, that is a funny thing here. These are the solutions of the wave equation in the internal direction. So, it is a Schrodinger equation. K is the eigenvalue of this problem. So, that K appears here and here, and this is just the Fourier transform in time. Okay? So, this is the complete 3-dimensional mode decomposition.
Sumit, I mean, expanding this thing in terms of the Z of nu.
Yeah.
There's nothing illegal here. I mean, you can do what you like.
Yeah, but what I am saying, it is not standard ADS. If you handed to me a scalar field in ADS, I would not have done that.
Yeah, I would have done Bessel.
Yeah.
So, what does it mean in terms of the IR boundary condition when you are using this Z of nu?
So, at the Poincare horizon, if I had a J, I have an equal combination of a cosine and a sine or some such thing. This just gives a cosine, whatever that means. I don't understand what it. I think that's one of the important questions in this. Okay. So, here are the solutions, and of course, you must have guessed the way we arrived at this is because, as Gautam says, we teach quantum mechanics in graduate school. This is a problem in quantum mechanics which are there in books, and so we just recognize that this spectrum is a spectrum. Okay. But there is a little twist to that which will come soon. So, these are the odd parity solutions, these are the even parity solutions, and this is the quantization condition for the odd parity solutions. This is the quantization condition for the even parity solution, and that is exactly that equation we have been talking about. Okay? It becomes exactly that equation if you choose V as 3, L as pi upon 2, and these are all in ADS units. Okay? So, the size of the extra dimension, it is really an extra dimension, it is the order of the ADS scale, it is not much smaller than the ADS scale.
Sumit, if I go back to the 3-dimensional Lagrangian involving the phi's, so from here, presumably you can say that phi should have a definite parity in order for the Z2 action to be a symmetry of this Lagrangian, or not. I mean,
No.
From the fact that you want to do a Z2 modding of this theory.
The Z2 modding of S1 just gives this interval, phi can have any parity.
No. If you began the theory, okay, with this kind of phi,
Yeah,
okay, on a circle.
on a circle, yes.
Yeah. And now you say that can I mod this, like in Morava-Witten, argues that his 3-form gauge field should be odd under that Z2.
Under that Z2, right.
Because the Lagrangian
So, I think in this case what that gives you are Dirichlet boundary conditions of phi at the ends, just as in Horava-Witten.
But it doesn't say whether phi should
No.
be odd or even.
No. No.
No, yeah. But phi should have some definite parity
Under that Z2,
under that Z.
yeah, so that odd parity. So, it gives you phi equal to 0 at the ends.
Right. Oh, sorry. Now this odd and even is with respect to the reflection about the delta function.
Yeah, yeah.
So yeah, good. So how are you going to yeah?
I am not going to do anything yet. I will just keep everything and solve the problem.
Instead of mod Z2, if you just said you have this finite interval with infinite walls at the two ends.
Yeah, then string theorists don't like it. They like things with modding things at various ways. So, I
But
think
I'm just saying to understand the spectrum.
that's what it is. Yeah, yeah. As I said, I mean, string theorists like orbifolds and things like that. So, I think it's better for them, I think. For me, this is good actually, that interval with the delta function is good. Okay. Okay. So, then you write down the action, and this is the form of the action, pretty much like that collective action which I wrote down. Nu naught square contains these Pm square which are solutions of that equation, okay. And I should say that I have only written for reasons which will become clear there's an additional term which are the odd parity parts. I've just removed, I've kept only the even parity parts here for reasons which will become clear now. Nu naught square contains that and that mass of the scalar field in there. Okay? Now, if I choose that mass precisely minus 1/4, then Pm square just becomes nu naught square, and so the solution of that equation is indeed the order of the Bessel function that appears, and that is what we wanted. For some reason, this is exactly the BF bound in ADS2. I have no idea what the significance of that is. There is a lot of black magic here. So, now that you have the modes, you can write down, calculate what the position space propagator of this theory is. So, this is the position space propagator written out in detail, integral over nu, integral over omega, sum over the modes, and once again this integral stands over a sum over discrete set and integral over the imaginary axis, and you can again go to this on shell thing, write in term, do the integral over nu, and you obtain this expression. Now,
So one question, is the delta function like completely, is that just one choice, or like is there some limit?
I should have engineered it to get the right answer. Okay, that's all. I repeat, this is a phenomenological theory. Okay. Okay.
Delta function with a specific strength.
That is 3. Yeah.
The V has to be
Right.
3.
Yeah. Okay. Remarkably, if we take this and evaluate at y equal to y prime equal to 0, then what you get is exactly that SYK 2-point function. In that SYK 2-point function, there was this object which came from the residue of the poles. Here that object comes from the value of the wave function at y equal to 0 and a combination of other things. Okay.
Y equal to 0 is where the delta function.
What the delta function lives. I will make a comment about that due to Witten pretty soon. And so, apart from an overall pure number, it exactly reproduces that thing. Note, in this framework, I have no reason to treat the m equal to 0 mode, namely that Pm equal to 3 of anything different from the others. In the SYK, that was singled out by the fact that there was a diffeomorphism invariance of the theory and so on and so forth. But so I have kept that actually. So, this answer is infinite. This is the answer which is really infinite. Okay. And we will stay with that infinity. Let us keep it that way.
So should
Why is it infinite?
Sorry, you just summarily discarded the odd modes.
Yes.
What's the kind of reasoning that you have? Well, first of all,
The odd modes I have discarded because eventually I want to calculate the object at y equal to y prime equal to 0. Then of course, the odd modes are 0 there, the wave functions are 0. So, it has a vanishing contribution to the propagator.
oh, in the propagator only the
Yeah.
Oh, so they don't appear in this calculation, they don't appear.
Yes, that is right.
Okay, cool.
So, it is interesting to look at why is this a divergent answer. You should expect a divergent answer, and it is divergent because this combination of Bessel function diverges at Pm equal to 3/2. Okay. Good. We are now going to calculate what happens to this when I include the non-trivial metric in the y direction by this factor a upon z.
So far you didn't include.
No, so far it was just, and it was divergent as expected. Okay. So, that we do by just very normal Rayleigh-Schrödinger perturbation theory. You write down that action with the d0 is the one without the a, d1 is proportional to a. So, you take the, in perturbation theory, all you need to solve are, in order to calculate the change of the spectrum, all you need are the eigenfunctions of the 0th order, and calculate expectation value of the perturbation in that. So, that is what you do, and hey, and this is what the answer is. So, the answer, the expectation value is this, where Q0 is that is the matrix element of that operator in that basis. And so, this is the shift of the eigenvalues, and again you notice it's A times omega, A is 1 upon j. So, it is omega upon j. So, it is exactly of the expected form. So, let us calculate the propagator by using this. So, I want to calculate the lowest order correction to that propagator. So, normally if you want to calculate the propagator, then you will need also the correction to the eigenvalues, eigenfunctions themselves, okay. But that is difficult. So, in principle you can do it, we did not do it. However, we are only going to calculate, in order to calculate the correction to this mode, the contribution of this mode, all you need is the correction, the corrected value of this mode, because that will give the leading answer. So, that is the one which we calculated, and this is the answer. And again, if you look at that answer, this is some product, now it appears actually a product of these Bessel functions, and then you recognize that J3 of is this combination. So, it exactly becomes that formula which I showed for Malthus and Stanford. Okay. So, it looks like that there is some consistent story here.
So, you not only have A some tilde equal to 1 upon j, but you have A equal to some, you can actually do the parameter fitting to let us say if you compare the low temperature free energy calculation.
Yeah.
I am saying that can you actually fit the parameter A to be some specific?
Possibly, except that we did not calculate what this Q0 is. So, I think you can.
From the underlying quantum mechanics point of view, before you turned on A,
Yeah.
why was there a divergence? I mean, you are sitting at where the repulsive potential is very strong.
Why is there a divergence? The divergence, as I said, is because the mode functions were divergent.
The propagator.
This function was divergent. That is what the divergence is.
So, even though you have a very strong delta function, repulsive delta function, the mode blows up there.
The mode at
The wave
any z actually blows up there. There is this one has a coefficient.
blows up at
So, I will show you. It not blows up at a certain location. This is this object. This is that function as a function of z. Okay? And this thing for any z, this blows up. And that is what you would expect. It should really just blow up for any z.
at y equal to 0.
I am only talking about the y equal to 0. I think it probably blows up for all y as well, because it is a property of these Bessel functions, nothing to do with the y things.
Because I was thinking,
So, does that mean you have a divergence even away from y equal to 0?
Yes, I think so.
Oh, I see.
So, this is the form.
so then the delta function is not that important for this divergence. I was somehow
Why is the delta function for this divergence is not caused by the delta function. The only job of the delta function was to get the spectrum.
So, what is from the point of view of so let's see. So, you have a quantum mechanics. You have the system in one extra dimension in a field theory, and you want to solve the spectrum and compute the propagator. Field theory. Why do you get this divergence from that point of view? Sorry, I can't say I fully understand.
Because you have picked a set of modes which were bad. If you want to pick a set of complete set of modes,
Okay, now I
so
understand it.
yeah,
Yeah, if I
which
had
turns out to be bad at that point. it wouldn't happen. No,
So this is true.
it is strange. But this is what you get, and this is what the SYK answer is also. Okay, so let me finish with a few comments. So the first comment is that, as Gautam has pointed out, the odd parity modes do not play any role in what I have done. So the day our paper came out, Witten immediately wrote to us saying that, well, you are not using the odd parity mode, so mod out by another Z2, so that you only keep the even parity mode, and Gautam calls it what? Horava Witten Witten. Okay. Okay. Okay.
But I see then you don't need a delta function.
But then you need some strange boundary condition at that point. You have a dirichlet boundary condition on one end and something which specifies the derivative at the other end.
Mixed Neumann division, is it?
Except that the Neumann, I don't know, Neumann usually fixes the derivative to 0.
Oh, this is
It's
not-
derivative to something. Okay, so it's something funny.
In terms of the field.
Yeah. I would like to emphasize, as has been quite clear, the propagator we have derived, which we used to identify with the fermion 4-point function of SYK, is a non-standard propagator. It's not the usual ADS propagator, because it uses this modes rather than the Bessel functions. In fact, again after our paper, Maldacena sent out a little note where he calculated he didn't quite understand it in the beginning that we are using this. It was not clear in the first version of our paper, it was clear to us. So he calculated the ADS propagator and found I don't find any divergence from this mode. And in fact, he showed that the standard ADS propagator differs from the one we have precisely by that factor of 10 pi mu plus 1, and so that's where the divergence comes from. So that's what you also said, if you use the Bessel, that wouldn't be there and this wouldn't.
But you know, that's just mathematics. What you are doing is correct. How could Maldacena and you get different results?
Maldacena said, forget about SYK. I give you a field to quantize in ADS, I use the standard mode decomposition in ADS.
The spectrum of an operator is also determined partly by the boundary condition.
That's right.
Exactly. So I'm saying that suppose you have this thing that this Dirichlet here.
No, it's a boundary condition in the Z direction,
In the extra Z dimension.
not in the Y.
Oh, I see. So you're saying that your infrared boundary condition is
Are different from standard ADS CFT.
I see.
Yeah, that's what it is. Yeah.
Yeah.
That's what is causing this divergence or whatever. Okay. So that's why it's somewhat different from standard ADS CFT, but that's what it is. So in summary, we have presented a phenomenological proposal for the dual of the SYK model. I'd like to emphasize what we have so far, use the background as a fixed background. I didn't talk very much about what the gravity sector is. To my mind, it's a bit unclear, because after all it is that 0 mode which should become the gravity. So I'm a little bit confused about whether there is a double counting there or not. It almost looks like that there should be a setup which is similar to a Randall syndrome setup here, with this thing at the delta function being some like a brain and using Israel-Stewart conditions. So there are of course many loose ends, but we think that this remarkable agreement of the spectrum and the propagator, including the 1 upon j correction, probably suggests that we are sort of on the right track. So probably some modification is needed to complete the story, which is good, otherwise I think nothing to do. Okay, thank you.
Just to take a slightly dissenting view, or else it could be
Yeah.
that if you try to get to near horizon ADS2 like situations from higher D, you don't get this fluctuating. This fluctuating, you don't get the PM equals 3 halves mode, the coordinate reparameterization. Because this reparameterization mode is the following. It says that take the boundary of ADS2
Okay.
and
Uh-huh.
make it fluctuate, two-time reparameterizations. And from a higher D point of view, whether it fluctuates or not is not a given. I mean, it depends on the situation. So if, just to go back, I mean, if I were just a straightforward ADS physicist,
You wouldn't have done that.
Don't do this, do JM, you get something very similar to what you're getting, but without that mode.
Without that.
And that would be a consistent quantization. And maybe.
But then I wouldn't have been able to compute this 1 upon j correction. See, that answer of this j, that the propagator was proportional to j by something, it precisely came from that factor.
I agree. So you wouldn't get the SYK.
You wouldn't get the
Something
SYK
similar
physics,
to
you
it.
get something else, yes. So it is tied to that. So I think that's very essential that it is there.
So tan pi by 2 pm minus 1, this factor that you had with j nu and j minus
Yeah.
does this have some sort of any understanding as in some sort of a phase shift kind of an?
It almost, it's not a pure phase.
No,
It's not a pure phase.
It's not.
For new imaginary it is.
Yeah.
It is a pure phase. I don't know I don't have a very deep understanding of that, unfortunately. But that's probably because I haven't studied those papers that carefully.
Yeah, but you also said it's sometimes related to the bound state formation, in which case it will not be a pure phase.
Yeah.
It just looked imaginary. It looked
So I can tell you what Polchinski and Rosenhaus did. They took the Bessel equation and so the problem was to diagonalize a kernel. The kernel is the kernel of small fluctuations of the bilocals, and so Kitaev had one of those eigenfunctions. Okay, so what Polchinski and Rosenhaus said that, okay, I have one of these eigenfunctions, so let's try to generate the others by SL2R transformations. Okay. So for that, the SL2R transformations have to commute with that kernel. That's how you would generate the other ones. And in carefully studying that, they concluded that these eigenfunctions have to be precisely of this form. So there is a reason for that actually, which is intimately tied with SYK. It is not something very natural in standard ADS-CFT. So I think our claim would be that the dual of this SYK is not normal ADS-CFT, it's something else, something different. And I don't have a nice slogan to say how different it is, but in terms of this formula, this is what it is. Okay. Yes, please.
So if I understand correctly, the fact that you have to choose a delta function potential, it's totally regardless of how exactly you break the conformal symmetry. Meaning, if I put this A dependence in the metric with some other gravity theory, so instead of using the dilaton, putting the dilaton of that answers in the metric, I use some other gravity theory, then nevertheless, I would, in your proposal, would have to put a delta function potential because even like in the J infinite limit, I would need to reproduce that spectrum.
That's correct. You know, the delta function is just required to produce that spectrum.
Yeah,
Yeah.
like the non-zero modes are correctly reproduced
Yeah.
in his thing just by the introduction of the delta function, which does not require that. So these two are two independent ingredients in his model, the A over Z thing and the delta function.
So the delta function is required for the spectrum. That particular combination of Bessel functions is to, I would say, is required to obtain the correct large J contribution of the so-called zero mode to the propagator, because that's where it comes from.
Suppose you were using the usual rules of I got a bit confused about this, but suppose you are using the usual rules of ADS-CFT and you take this particular combination of modes, would one say that one is turning on both a source
And an expectation value? Yes, probably. Yeah.
so maybe that is the
Well,
expectation
not
value.
quite, not quite. Hang on, not quite.
Yeah, I'm
not quite. This combination of modes for real values of the order of the Bessel function,
Vanishes.
that it vanishes, the j minus doesn't, it vanishes, okay.
That's why I was confused.
Yeah.
Because there it seems it is purely normalized.
It's purely normalizable. After all, it's they proved it's a complete orthonormal set.
Yeah, but then it is having an effect for your imaginary. This one.
I think it is a, see the in the standard ADS-CFT, what there's some kind of regularity condition in the horizon which you use, okay. So for example, if you were calculating retarded propagators, you would use a purely ingoing ingoing waves at the horizon. If you are calculating a Feynman propagator, that's not what you would do. I mean, you would use this just the Bessel functions, which is an equal amount of ingoing and outgoing waves at the horizon. This is some so j nu is a cosine and a sine together, and this one somehow gets only the cosine. I don't know what it means. You know, the Hankel is only e to the I, right, and this combination at z equal to infinity only gives the cosine. Might have some interpretation. Sine is also equal amount of incoming and outgoing. It's just a phase difference, yeah. But it's only thing I can say, it's you can, if you were to take a z going to minus z, I mean sometimes you want to attach the z equal to infinity with some another space time, maybe there is some interpretation, but I don't know really. It's some funny thing, but I think it's a key thing in the dictionary. So I think we should probably understand this.
But I would have agreed with what Sandeep is saying, is that in a Euclidean ADS, at least, there if I demand regularity at the IR, then the relative strength of J nu and J minus nu is completely frozen.
Sure.
That's what gives me the Green's function.
There is no J mu there, there is a K.
Yeah, sorry, K. So the relative coefficient between K nu and K minus nu is fixed by that property.
That's right.
And presumably this regularity is replaced by ingoing or whatever. I mean,
That's a purely ingoing
as soon
thing.
as you are going to Lorentzian signature, it seems that there are so many different kinds.
Of course, that's right. So many different kinds of propagators. Yeah.
And it's only one of them which corresponds to this relative
SYK.
strength of tan, blah blah. So it's I see. So it's a particular linear combination of advanced and retarded.
That's correct. Right.
I see.
Which is not the usual.
Which is
So
not
that's the homework exercise. To figure it out, what does it mean?
Which is neither Feynman.
Yeah,
nor
Pranjal,
retarded
yeah.
nor,
I have a comment regarding this. Like a possibility that could happen is like
you're back.
we know that modification of the boundary conditions sometimes correspond to higher trace operators being introduced, perturbation by the higher trace operators, right? And in this particular,
That's usually a boundary condition at z equal to 0 that is changed by higher trace operators, right? Yeah.
but could it possibly correspond to some higher trace perturbations in the IR only? Because here
You're changing the horizon boundary conditions.
Yes.
Horizon, but I mean his point is also that can't you change like this alternate quantization changes the boundary conditions at
At the boundary.
the boundary,
Right.
You mix up source and but that's not what you mean.
Maybe something special happens at the Breitenholler-Friedman bound. Does something special happen in ADS-CFT?
No, before that also, right?
No, before that also, but exactly at Breitenholler-Friedman bound, is there something funny which happens?
Yeah, there are some singular.
Yeah, there are singular stuff actually.
Singularities at
Yeah, I think
We
so.
always avoided that.
Yeah.
Is that right?
It was never clear to me how to treat ADS-CFT exactly at that bound.
Okay, I didn't
Other
realize.
motivation I had in saying that was in the particular construction of Jevicki and Jungi in their paper when they tried to write the action in terms of bilocal at an intermediate step when they integrate out the J fields first, the disorder integral.
Yeah.
They have a quartic trace type of term that they
Right,
have.
right.
So it might have some connection there.
Because you actually get a trace psi to the power fourth in that action.
Yes.
So maybe you are saying it's showing you there is a, if you want to get away from this, so keeping just that you are forced into this. If you want to get away to this from this, you should have a trace, but there is no trace psi square.
Yeah, in these models, you inevitably have this
Right,
four
right.
terms.
No, but you might be saying that how about having a trace psi square whole square? But trace psi square is 0, no? Psi square is 0.
No, it depends on what multiplies it. If you still multiply that by some some coupling, then it's okay. You can have trace of psi I psi j times trace of psi k psi l, whatever, and then it multiplies. It depends on how it feeds back into the final string of text.
I guess so.
It's possible to invent such a thing.
So that would be another homework exercise. Invent a model which gives standard ADS-CFT in this language. Huh?
Standard AD, but you mean in 2D in ADS2? Is that what you
Oh, this 3D is only giving the Kaluza-Klein tower. Let's keep it that way. By standard ADS-CFT, I mean propagators which are Bessel functions only, J's.
So that's, I thought if we impose the usual boundary conditions at Z going to 0.
No, invent an analog of the SYK model whose propagator gives you this. That's what I'm saying.
That's it.
Maybe there is a model.
Isn't that model take, okay, sorry, you want to take SYK and throw away the time reparameterization?
No, it wouldn't.
No?
Because if you threw it away, you wouldn't get this enhanced propagator. You want to get that. If you threw away completely that one, there is a large contribution to the SYK propagator which comes from this mode. Okay? That large contribution appears to be infinite if you are working at j equal to infinity. But you have to reproduce that. That's an answer.
Oh, so you want to keep that?
Yeah, yeah.
Yeah, because
You want to keep that? Oh, I thought you were saying do the maybe I misunderstood your question. I thought your question was do the standard boundary conditions in your model and then change SYK to get the same answer. That's not what you want.
Yeah, but you cannot just say take SYK and remove one of the modes. I mean, you have to write down, some Lagrangian where this is automatically not there.
yeah, I mean that can only be done if there's some kind of gauge in which gets rid of. But the usual thing does not have it. I mean, it's really a singular CFT.
Yeah. Okay.